Hello.
Hello, Ma. Hello.
Hey,
Hello.
how are you?
Good, good, good.
Okay, good to see you. I have to upload the file again.
Okay.
For this one. And thank you for joining. Did you join also the other one on avatars?
Oh, I wasn't able to do that because I still had some school work earlier.
Yeah,
So yeah, I'll catch up later. That one.
yeah, it was
Super
good.
interesting.
Yeah,
Oh, nice.
I think it links to the work we need to finish.
Yes,
Right.
definitely. Yeah. Right.
Okay, let me see. Stop. Rogue. Let's see if I can upload this one again. Okay, let's see. Do we have people waiting or something? Oh no, everybody's here. Good. Sorry, I didn't realize everyone was already here. I was trying to put the Rackrook. Actually, Dieter, since you're already here, I couldn't upload your paper on the Discord. Is the only one missing because it's too heavy, and when I reprint it, it gives zero key. There is a link there that you can go and find the paper, but I wanted to have the papers there just for easy access.
Yes, I'll just paste the link to the GitHub page, which also has the latest version of the paper in the chat.
Yeah, I'm trying to put all the GitHub links also on the workshop page. The idea is that it becomes kind of a living repo of you know, the content even in the future. So I'm gonna share my screen very quickly. We're gonna wait a little bit to see if we get more people. Okay, Eric and Matias are here. Anthony, I think he's here also. So I'll just start with a short intro, and then I thought this workshop was best organized if we give time to people to present their actual source and you know, tools, so the rest of us learn about the tools instead of having many panels or so. So it will be mostly around that. That's the program. And I think all of the organizers, we agreed on that. All of us read all of the papers. We really like the different taste of them, and it gives an idea of what things are worrying the community, which are the problems, because perhaps more than one group are trying to solve a similar problem. That means that, you know, it's a high problem. and then some very interesting tools. So we end up accepting almost all of them, and we hope we can learn from this. So this is the program. We're going to start with all this idea of data capture, analysis, and understanding of scenes. How do we record what's happening, and how do we infer from what's happened? Then we will have a bit of perception and cognition. Source tools, I called it this way, but you know, they are on different fashions, each of them. I think they're very interesting. Then authoring and access of the content. and then some tools for avatars. I'm trying to add the videos. If you have a short video, send me of YouTube and the links to the repos in the website. So just send me all of that if you have it available. And the reason why we're doing this open sourcing is because a couple of years back when Anthony was here at Microsoft Research as a visiting researcher, we thought of, man, we could release all these Rocketbox avatars, and it required a lot of cleaning and fixing because some things, it was a bit of an archaeological work, right? The Rocketbox avatars were existing in the past, they had disappeared. I found out they were somewhere in Microsoft, and then that's how I revived them. And after that, we of course released the library, and then we released more tools, right? All these assets need, it's not just you drop an avatar, you need to animate them, you need to be able to control them, to have interactive experiences. So that's been my main focus on open sourcing in the last years. It's been to provide tools for the Rocketbox avatars, but also in a way that they follow standards, so they could be used for other things too, right? So these avatars have this kind of very interesting thing, standard skeletons, which means you can transfer very easily from one to another. And actually, ever since the release, now it's available for everyone with MIT license, right? It's not only for research and academics. So if you want to have your company use it, you can also use it. And then we released this other tool for animating avatars with a super simple lip sync, and using, this was done in 5 minutes. So it's very fast. And you have like 3 different types of inputs, either from the Kinects, either one can work. From offline video, this is more like a parser from the Vive 3D, but now, for example, we're working to have a map to MediaPipe also. So the complicated thing here always is remapping of the skeleton, right? It becomes quite a painful thing. And then we have this kind of live system for embodiment, so to say, and it's a separate, so these are the 3 separate projects you'll find in the repo, and it's providing you this embodiment experience. And if you have the Quest or MRTK, you can even have the finger tracking. Different aspects of the things we can do, rescale to the avatar. And then the most important thing is you can record and play back animations, right? And everything is inside of Unity. So you've recorded an animation, you can play it back. Here, a bit of the comparison between Kinect V1 and Azure Kinect. Of course, Azure Kinect has a 3D type of experience versus Kinect V2 is only 2D, which means we had to do some sort of data compensations because we know what the correct position is from the original data set. We can fix problems that the Kinect has. Still, there are problems like turning around, still there. Yeah, and you can use that to put a lot of avatars. And today we will speak more about this, but we now have added blend shapes. And this is the one of the projects that we will present today. And with the blend shapes, we're releasing this other toolbox to animate facially avatars with vision and lip sync. And Matias will talk more about that. But anyway, so all of this journey has brought me to this. So we need more tools, more open source tools. We can create a large community of researchers that collaborate. We don't reinvent the wheel. And we also, if you think of all the people who are doing VR research independently, if you put them together, man, I'm not sure any company in the world can beat that, right? So it feels very interesting to explore how we can work closer, everyone. And then also bring people from other fields. A psychologist is not going to start doing quaternions. So, it can start having applications. So with that, I'm going to leave the room to the first presenters of the day. And so we're going to start with Dieter presenting RAGRUG, which is a paper that got accepted as a full journal paper. And you can find it also on GitHub. Okay, can you present, or you need some sort of rights?
Host disabled participant screen sharing.
Okay, okay,
so
I'm gonna
you need to let me.
more. Okay, you're a co-host now, so you should be able to present. And I'll go.
Okay. Can you see my screen now?
Mm-hmm. Correct.
Okay, excellent. Well, so I'll get started. I understand I have 15 minutes or less, so I'll try to make it short and sweet. I'll talk about RAGRUG, which is our new toolkit for situated analytics. This is joint work with my PhD student, Phil Fleck, who goes from Graz University of Technology. And I think a keyword was already given by Mar, which is do not reinvent the wheel. If you're trying to address a complex problem in VR, AR, or any other advanced software environment, it's a good idea to steer clear of proprietary solutions, which are then only a lifetime for only one academic experiment that you're doing, and then your PhD student goes away. So that's a recurring problem. And I mean, some people in this audience may know me. 20 years ago, I was working on Studierstube, which was a large software framework which died a silent death of software aging at some point. And tapping into existing live software ecosystems is a much better idea. Now, having said that, the topic here is situated analytics, which I believe is an up-and-coming field. We now see a lot of work on what is called commonly immersive analytics. That would be interactive visualizations. And I really mean visualizations of any kind of data, in particular abstract data, in an immersive medium, such as VR or AR. And in contrast, situated analytics goes a step further by bringing interactive visualizations in typically an augmented reality environment, which is grounded in reality. So we're getting away from purely virtual stuff, and in particular, Wesley Willett gives a definition in this really interesting paper. Saying situated means in perceptual proximity to a physical referent, where the idea of a referent is that the referent is a meaningful physical object close to the user. So if you have an X-ray visualization of cables buried in the wall, we would call that situated. Whereas if you have a chart of product sales or just a web page, as in the Microsoft HoloLens, promotional videos, glued to the wall, that would not be situated because the product sales have no relationship to the wall, right? Whereas the cables have. So referents are really important when you're trying to do interactive visualizations grounded in reality. And these can be either passive reference or just things, but also active reference. And this brings us to this Internet of Things domain, where things get even more complicated. Now, let me start from a traditional visualization pipeline, a desktop visualization as it exists now in products such as Tableau or D3 on the web or something like this. What is going on there? Everything happens in the virtual world. You have some data called a virtual model here, which is transformed or visually encoded into a data representation. This is then rendered and displayed on some display, and then the user perceives it. And only that last step, the perception by the user, is actually happening in the physical world, right? There's nothing else that is not purely virtual. And even the interaction is virtual or abstract, if you want, because you can only relate with mouse or keyboard, let's say, to this abstract data. If we go into situated visualization, the whole thing changes drastically. So you see 3 red boxes here that I've marked up to show what changes. The first thing is that the display becomes a situated display. A conceptually situated display becomes part of the physical environment. We've moved the display from the virtual world into the physical world because it's now perceived together with other aspects of the physical world. And these other aspects of the physical world are, of course, the reference, which are now subject to any kind of physical interaction. So in the real world, you can change it by moving furniture around, by opening a cupboard, by, I don't know, eating an apple even. And the reference establish a physical context. So they need, we need to know about this physical context. We need to sense or detect what is going on in the real world, or we need to be able to perceive data that comes from streaming sensors, Internet of Things, and the like. This is actually an idea that is very similar to ubiquitous computing, but augmented reality affords much more fine-grained spatial interaction. This is maybe the most important aspect here, and then we can register visualizations to the real world based on that physical context. And the third aspect is the physical virtual model, which is usually absent from any kind of visualization application. We need a systematic way of storing the aspects of reality for which we want to deploy the visualization. And that's not really a new idea. That's already something in the mixed reality continuum proposed by Milgram and Kishino. Everybody always quotes how it's about the output side, mixing the real and virtual in the output, but it's also talking about, the paper is also talking about the input side, where it's called amount of world knowledge that is available. And this is what would go into the physical virtual model, or today we may be calling it a digital twin if we use industry jargon. And now from these considerations, we arrive at 6 research challenges, and I'll just, they are all tied to some aspect of this sort of situated visualization or situated analytics pipeline. The first question is how to deliver visualizations in VR or AR. The second question is how to create the visual encoding, which is then presented in VR and AR. The third question is how to make these visualizations or visual encodings context aware, aware of reference. And the fourth question is how to create a physical virtual model for the information that we just have to know, that is not streaming in as a context-aware variable, but that is sort of a static aspect of the physical world. And the fifth question is, how can we make the visualizations actually react? How can we make it reactive to changes in the real world? And the sixth question is about how can we author the whole thing? And in the interest of time, I will only be sketching some of the core ideas here. So the first thing, how we deliver visualizations in VR and AR is really trivial. We use Unity, we use OpenVR, MRTK, the typical collection of libraries. That's not a novelty. The second question is also easy. There are now toolkits such as the Immersive Analytics toolkit, which do a good job at creating visual encodings for VR and AR. And we are just wrapping around that. Yeah? So with IETK, you get the visual encoding pipeline that uses the typical grammar of graphics that is also prevalent in contemporary desktop or web visualization systems such as D3. Only it now targets shaders, geometry shaders in Unity, so the whole thing is fast and you can do some 3D interaction. That in a nutshell is what IETK will do for you. But what it won't do is the rest of these things, the questions that I've labeled question 4, sort of 3, 4, 5, and 6. And the first one is how can we address the context awareness? And the context awareness is already addressed in the Internet of Things world, usually via some sort of data flow that lets you coordinate sensors and control systems and so on. And data flow is easily accessible with sort of low-code interfaces by visual programming, drawing these node link diagrams as shown on this in the figure here. And then the scripting language can be used to do some custom behaviors inside that. This is state of the art in the Internet of Things world. What we're using specifically is Node-RED, which is a very widely used open source IoT framework. Again, don't reinvent the wheel. The Node-RED guys are already doing all of that. They are doing visual programming. They are doing network communication. They are building a whole web stack with Node.js, so you can attach an HTTP server and databases, various SQL and non-SQL databases. All of that is already integrated into typical Node-RED configuration. So we have a place to put the physical virtual model as well. So that's really nice. And that solves some of our questions. And now the only remaining thing that needs to be done is putting those things together. And this is where the main contribution of RegRag comes from. And a unified and integrated access to all these features. So what you see here on the left-hand side is the Node-RED framework. And what you see on the right-hand side is the, situated analytics client that would run on top of some AR, VR hardware and Unity. And what you see in orange here is a typical visualization pipeline with the steps of data. Visual encoding number 3 and rendering number 4. So it's a fairly standard visualization pipeline which can now flow through these existing software infrastructures with some extensions that we've done. And in particular, the novel and important aspects are a reactive programming extension to IATK. So IATK can now react to data that is coming in real time. The visual output of IATK hasn't changed, but its ability to react to data changes has been added. And the second is that we roll out a Node-RED-like data flow across the entire system, including Unity. So the C# layer of Unity is still accessible, but it's completely dormant, and everything is written in Node-RED-like JavaScript data flow, which is very low code, which is very easy to get into, including the visual encoding capabilities and everything else. And we just connect everything together and we end up with a really nice uniform programming model, which also addresses the situated authoring needs that we feel it has. Because now what happens is you fire this up, you use the visual programming tools that come with Node-RED, but they deploy across this entire distributed system, and JavaScript code can be reloaded on the fly everywhere. So as a result, when you want to change something, you don't have to shut down the system, recompile, and then redeploy. All of that, it's even easier, from the old days of C++ code and the long development cycles. People are now used to C# and relatively swift compilation times, but doing that in JavaScript with data flow is even still much faster.
Dieter, just one question.
Yes.
Many more screens or?
No, I'm done. This is basically awesome. It. I can play you a video, and this just shows some results that we have.
Awesome.
But maybe we want to do that with you can already start asking questions if I don't play the audio here.
And also, I just uploaded the video to the website.
Yeah.
So you have it there and the link to the tool.
Yes. So I'm happy to take questions already. If you want to know the details about these examples, just read the paper or watch the video again with audio. Okay, so if nobody is wanting to ask a question now, here you see our basement where we've custom installed some sensors because we don't have the real ones. But what you see here are visualizations which are created on the fly based on a description of the basement infrastructure, which is read and passed in real time from a physical virtual model. So if you put new sensors in, they can even register themselves automatically over the network with the database, and then visualizations, default visualizations will pop up. They may not look super pretty yet, but they are completely functional and you know, could be much more complex. So this is another example where if you ever been to the Museum of Pop Culture in Seattle, they show lots of record covers. Yeah? Now, the record covers are a reference. This is probably the most dynamic augmented reality authoring application that you've seen so far. We have hundreds of records covers there. And this is an immersive analytics application called Stream that we re-implemented. And the original implementation, we could throw out half of the code because it's already covered by the infrastructure that RegRock is providing. So this was a sort of an external study to see if complex behaviors can be replicated with the given tools, and it did work out favorably. Okay.
Okay, sounds good. I mean, we will have a bit of a panel at the end, so more people can ask questions there. I would like to welcome Sean Andres to present the next work, on situated intelligence. And also you can find more information about his work and the open source tool already in our workshop page.
Okay, thanks, Mar.
Thank you.
Let's see if you can all see that. Cool. All right. So yeah, thanks, Mar. Hi, everyone. So like Mar said, my name is Sean Andres. I'm a researcher at Microsoft Research in Redmond, Washington. And today I'm just going to tell you guys a little bit about an open source framework that my colleagues and I have been developing called Platform for Situated Intelligence, or you'll hear me call it PSI for short. And I think Dan is also on the call, so we can maybe jump in and answer questions as they come in. And as you'll see, the framework is pretty general. It was designed to support the development of a fairly broad class of systems, but we've recently extended PSI to include specific capabilities and components for targeting mixed reality applications, which is why we wanted to talk about it today. So today I'm just going to present a high-level overview of what PSI is and how it works, and then talk a little bit about how it might be useful for mixed reality researchers and developers. So first, why is it called Platform for Situated Intelligence? It's a software platform that people can use to develop systems with. And we created it originally as shared infrastructure in our own research projects in an area that we call situated intelligence. So in our research, we like to build and study systems that reason about the 3D world that they're situated in, whether that's physical or virtual, and that have to interact in real time with humans that inhabit their world, often using natural language. And so that's a broad definition that points to kind of a general computing paradigm with a lot of possible applications that more and more people are starting to get really excited about. So everything from systems that support collaboration and learning and training and mixed reality, to embodied agents and avatars, to physical robots that navigate human environments and have to engage in social interaction, smart meeting rooms and instrumented factory floors, and there are many more examples. And a lot of our past research has involved social robots and embodied agents on screens, but we've recently started getting interested in mixed reality scenarios. And being at Microsoft, we've started looking into leveraging devices like Hololens 2 in our research. So Hololens 2 is an AR device that allows you to render holograms, and it uses environment. And a lot of the existing development tools, it seems both in-house and external, they really focus on making it easier to create and interact with content rendered to the headset, which is super important. But what's really exciting about devices like this, at least to us, is the rich set of multimodal sensors at your disposal, right? So you have outward-facing cameras, you have microphones and IMUs, You have head and hand and gaze tracking. You have access to world meshes and basic inferences about floors and walls and surfaces. And all of that combined can really enable interesting research and applications around, things like egocentric perception and recognition and understanding everyday human actions and activities, tracking objects and object manipulations in 3D, just to name a few ideas. But unfortunately, it's still quite difficult to build complex end-to-end applications that can fully leverage and combine all of these streams together. And often you at least need to build a basic prototype before you can get into some of the research questions that you find most interesting. And that can be a big barrier to entry. Right, so you quickly run into all sorts of engineering headaches, bringing together different kinds of components and technologies that were developed in different places. The application often has strict latency constraints, usually because it needs to be interactive. Fusing and synchronizing data across streams is non-trivial. For example, if you want to combine IMU data that's really high frequency and low latency with scene understanding results that are low frequency and have high latency, what's a good way to do that? And then in the development cycle itself, it's often useful to be able to collect some data once and then quickly rerun over that data as you iterate and tune the system, rather than constantly needing to deploy to the headset and have a live interaction every time you change something. And being able to visualize collected data in different ways to debug your applications is super important. And all of these challenges, by the way, they apply not just to mixed reality, but all kinds of situated interactive systems like robots and so on. So we built Psi exactly to address those sorts of engineering challenges, again, both to accelerate our own research and help other researchers and developers in the community. It's open source, available on GitHub, and it's developed on .NET Standard, mostly C#, but we have examples of how to interop with other ecosystems and languages like Python. And so I'll spend the next few minutes just giving you a quick high-level overview of Psi in general. And then I'll say a little bit about the new mixed reality support we've recently added, mostly targeting HoloLens 2 for now. So for example, the video on the right there, it's a 3D visualization captured from a little sample app you can find on our GitHub, just meant to help people get started with using Psi for HoloLens. So as a framework, Psi can basically be broken down into 3 layers. There's a runtime infrastructure that takes care of low-level things like streaming and scheduling component execution and logging. There's an open ecosystem of components which can be plugged together to compose an application. And then there's a set of companion tools for debugging and visualization, data annotation, and offline analysis. Let's start with the infrastructure. So Psi applications are basically directed graphs or pipelines with nodes and edges. Nodes are the individual components responsible for particular units of computation, and the edges are the streams that carry messages between components. So this is a simple example of maybe a small chunk of a larger app responsible for detecting the source of speech by combining a microphone connected to a voice activity detector and a camera connected to a lip movement detector. And the code on the right kind of shows how it's easy to instantiate a pipeline, instantiate these different components, wire them together, and then execute it. And then once the pipeline is running, the infrastructure handles stuff like scheduling and coordinating the parallel execution of those components and passing the messages around over those temporal streams. And there's a lot more detail here. I don't have time to get into about how it does that efficiently, how the developer can control the queuing of messages on these streams, when to drop messages when components can't keep up, and so on. Time is a really important concept in Psi. So messages flowing over streams are time-stamped with an originating time at the source when the message is captured in the world. So for instance, when the camera produced that image or when the microphone picked up that bit of audio. And then this originating time is automatically carried forward as the message is processed by downstream components, which means that all of these components can be latency aware. And then because this component knows the latency of each message as it receives it, it can then pair them correctly according to what the developer wants and according to when those events happen in the world, not just when they happen to show up at the component. Data from any stream can be easily persisted to disk where desired. And the infrastructure tries to optimize for throughput, so any logging doesn't hinder the actual performance of the live running system. And then, because the timing information is retained when logging, that enables reproducible data replay, where you can rerun your pipelines and do experimentation from persisted data exactly as it would have occurred when running live. So in terms of components, this is a page on our GitHub site where you can find a list of available components for various kinds of sensors, components for imaging and vision and speech and language, wrappers for ML models, and some pointers to external repos where people have shared their own side components that they've created. And so the idea is that you can rapidly develop new applications with few lines of code by plugging together existing components and maybe writing a few of your own, which is also easy to do. And to illustrate that, we have a sample application on our GitHub with a tutorial that kind of walks you through all of the key concepts with the goal of building an app that can identify objects when a user points to them and speaks the question, what is that? And it uses a depth sensor, an RGB camera, and a microphone. So basically the sample shows how to take the sensor stream of depth maps, pass that to a skeletal tracker, compute a line extending out from the arm's pointing direction, intersect that line with the depth mesh, project that intersection point into an RGB camera and crop a window around that point, send that cropped image to an object detector in the cloud, and in parallel compute speech recognition results over microphone audio. And so this sample currently assumes an Azure Connect for the sensing, but it would be fairly easy to adapt to something like a HoloLens scenario, just swapping out where the source streams are coming from. And then really critical to developing these kinds of applications are the support tools, particularly for data visualization. So, if we zoom out from that sample app I just showed, you can see that those images were actually captured from a data visualization tool included in the framework called SciStudio. And this is a very general tool where you can visualize data in 3D or 2D or on timelines, depending on its type. And you can scrub around through the data, zoom in and out, pan around, set start and end points for playing back a particular sequence, and all kinds of stuff. And you can also connect SciStudio to a running application for live visualization, in addition to just visualizing data you've previously collected. And there are other features like for batch processing and data annotation that you'll find there. So like I said, we recently released an update on GitHub, which includes specific support and examples for developing mixed reality applications, particularly targeting HoloLens 2. We leveraged a couple existing open source toolkits in the process. So StereoKit, mostly for rendering and UI stuff, and then research mode on the HoloLens, which gives access to some of the lower level streams that aren't exposed out of the box. But basically, we created modular side components for all of the sensor streams, and then output components for rendering holograms and spatial sound. And then now the idea is that you can use those input and output components and plug them together with any other components you want to create your own end-to-end SCI applications that run live on the HoloLens. So for example, here's a visualization from some data collected by a little, like a language learning app that we built just for fun to kind of test all this out. So the goal of the system is to put labels on objects in your environment, showing their name in another language as sort of sticky note holograms. So on the bottom, you're seeing the user's head pose, the gaze rays, an orange ray here, the projected camera view, and the depth map all coming from the HoloLens. And then the upper left is showing where the gaze ray intersects with the camera. Again, we kind of crop an image around that intersection point, send that to an object detector that gives us an English label for that object. And then that English label is sent through another component that does language translation. And finally, we get a label in Italian or whatever language that you want. And so on the upper right, you're seeing the user's view from the HoloLens. It's kind of hard to see, but there's like a little sticky note there with the translated label floating. And it's now fixed to that 3D point in the world where the gaze was pointing. So if I play that, you can just see how this is all continuously happening in real time. And as you look down the room, more sticky notes pop up with labels in another language. And many of them are wrong, and whatever the cloud components can produce. But it's just another simple but kind of fun app that it's, again, easy to write with maybe a couple hundred lines of code, and just kind of shows what's possible. So if you're interested to learn more, try it out. Check out our GitHub page. We've got lots of documentation, videos, pointers to some workshops and tutorials we've run about it, and a repo of samples which you can try, including, again, most recently, some more samples showing how to use Psi with HoloLens. But I'll stop there. I'm happy to take any questions.
Thank you, Sean. Any questions? And also, you have access to a direct link on the workshop page. If there are no questions now, we will move on to a Stack by Aria, and we will have questions on the panel. I have questions.
Thank you, Mark. Thank you for that kind of introduction. Can you all hear me all right?
Yes, we can hear you.
Same as screen. Okay, got it. Yeah, I apologize for sort of a bandwidth issue at my end. So I'll try my best to present. And if you have any issues, just let me know. So this was sort of a progress. And basically what I'm trying to say is, like, when I first saw Mars tweet about this, open source toolkit workshop, and this was something in the works, and I haven't had like a solid plan to release it, but I thought, might as well write about it and see where it goes. So my paper is basically a tool for real-time replay and analysis of spatial trajectory and gaze information captured in immersive environments. And by that, I mean just this video. So this is part of an ongoing investigation study. It's actually the fourth iteration of one of my many studies here at Emory, originally continued from the University of Georgia. And so my video is playing. Okay, so what you're looking at here is a top-down view of a decently complex maze, not too complicated, but the whole point of this maze is to get in and get out, get some tasks done. So this has a twofold task. You have to find a minimap, and you have to go find an avatar and rescue it. And so, so what you're seeing at here is a replay of a player. I don't know if you can already tell. It's a gamer, a player who's gamer, an avid gamer, solving the maze. And then on the second iteration, you'll probably see, you'll see another person solving the same maze with the same task set, but this time, this person is a non-gamer. By that, I mean a person who has not been exposed to video gaming a whole lot through their course of life. And so, while working on these, various factors, which I've worked on before, this was part of a technical factor impact on user performance. So my question was, if there is a significant impact on users' behavioral ability to successfully navigate a 3D maze under the influence of factors like immersive and non-immersive 3D UIs. And so basically what that means is that I'm comparing navigational performance and somewhat behavioral performance by pitting the same maze, but with different immersive and non-immersive 3D UI. So in one setting, the person is inside the maze through an egocentric perspective, looking around and solving the maze as they would do normally. And then the other one is a mediated degree of order. So basically, they're solving the same maze, but this time they're using a non-immersive 3D UI. And by that I mean they're basically playing the game on a giant virtual screen inside a virtual. So the top and bottom set. And so real quickly, before I get to the stack toolkit, what we did was this was a 2x2 crossover. There were two conditions. We deployed immersive deployment first, the immersive 3D UI first, and the non-immersive 3D UI second, and then flipped the order. And we collected these qualitative data. So we had demographic data such as age, gender, vision, self-reported athletic score, self-reported gaming hour score, and then the similar sickness score and presence score. And so this is where my motivation stemmed for the stack toolkit, because while I was trying to dissect human navigation in immersive settings, I repeatedly saw those patterns emerging over and over, where if a person reports a higher gaming score, in other words, a higher number of gaming hours scored per week, then that person has a very distinct trajectory signature, if I want to call it that. And then whereas the others, people on the other spectrum who have not at all played any video games or very little video games, even those that are considered mobile video games, they have a distinct pattern. And so that led me to believe that there are features of the user trajectory that we could use to predict solvability or predict performance in an online fashion if there's enough data about that person. And so by intuitively looking at the data and through the stack toolkit replaying over and over again, I was able to deduce these 5 features. So the distance traveled, the coverage, the number of decisions points reached, positional curvature, and head rotation amount. And the positional curvature is basically the signed angle of the curvature. So basically it shows or denotes smoothness. And then the number of decisions points reached is basically, particular to this maze, and I'll try to kind of like put the argument where that it could be scaled to other mazes and other settings too. But for this particular maze, these red spots or zones are the places where you have to make an active decision of strafing in any direction or going in any direction. So, so those were my features, 5 features. Now, so I'll take a break at this point and I'll show you my work in progress Unity scene, if you can already see it. Start with the basic scene here. And so I call it the maze replay, and when I play it, you'll see just this person is a randomly selected user, and you'll just see a quick run of that person through the maze. And by the way, these are replays of actual human data. So these were subjects randomly chosen from my data set.
Okay, sounds great. Yeah, when I saw this, I was thinking of the, maze that they create for rats, but there is also a virtual rat maze, which is crazy. But yeah, they put rats on an Omni track and they put them on a virtual reality. So I was thinking of that the whole time when I was looking at this. Okay, so
my point overall, more is this, that this tool can be scaled up to any setting, and then you can just, once you have the human data set with you, you can start replaying the data using these scripts. And you can go to a deeper dive. Like I said, I'm trying to understand coverage. I'm trying to understand skills versus chance, based decision making. So this one is one of them. So so there's a lot to it under the hood, I think, and there's potential, I believe, that this can be taken and scaled up to other generalized settings. Yeah. And real quickly, I wanted to give you just a peek into my my path forward. So what we're trying to do here is to develop a generalized model of human spatial navigation. Again, to contextually do these simplified mazes first. I mean, it's incremental in nature, where we can, I would really like to include like levels and other complexities of the maze. But basically, we're working on defining more features of spatial navigation trajectory observed to human intuition, using LSTM neural networks first. And then the other thing I chanced upon is this spatial temporal Bayesian modeling, maze runners. And so I'm trying to, and this is another open source toolkit, the INLA, the R integrated nested Laplacian approximation. So I'm trying to kind of like merge these two to come up with more, hidden features of spatial navigation that might, give us a better insight as to why and how people, take some certain decisions.
Sounds good.
Stop my sharing and take some questions.
So we're gonna move to the last presenter of the session with the excitometer. Again, it's also accessible on the website. Luis. Yeah.
Yep. Can you hear me? Can you see my screen?
Yes.
Okay. So, hi everyone. I'm Luis Quintero. I'm going to present the excitometer. So it's just it's an open source Unity plugin to analyze heart activity and movement in virtual reality environments. So we could initially argue that a primary goal of virtual reality applications is to enable experiences that are both engaging and useful. But what every user considers engaging, useful, or exciting, in this case, depends on individual characteristics. So that's why many researchers are interested in analyzing subjective human factors in virtual reality. For example, find relationships between the visual stimuli that you are having and emotions or perception or other behavioral patterns. So to assess human factors in VR, it's common to rely on user ratings. So you have a set of questionnaires that participants are going to fill out during the experimental sessions in VR, and then they provide feedback about subjective cognitive factors, if they felt presence, or if there were emotions that were elicited by the environment, or if something from the environment was specifically striking. And these user ratings are in general very useful. But they have some drawbacks because then for VR, when you're applying questionnaires, it breaks immersion. Questionnaires are often prone to biases because they rely on the user's memory. And you can only collect limited data samples, the amount of questionnaires you administer during the experiment. So in our research and other research fields, we are trying to include bodily data also in virtual reality. And we think that this is a crucial step to enable like a better understanding of human behavior in VR. But because it allows to capture internal and external dynamics from the user. So you can capture movement, but you can also have some physiological variables. And you can collect data uninterruptedly. So you have wearables that are non-obtrusive, and they can collect data during the whole session instead of just on specific time points when you have the intervention. And these are not mutually exclusive, so you can have bodily data to complement still the user ratings that you collect through questionnaires. But this integration has multiple challenges. The first one is quite technical, and it's how do you integrate data that comes from external sensors into the existing virtual applications. So it's different to have sensors that are already embedded in the headsets than to have wearables or like an external entity. And even if you include this data, there's a problem with domain expertise, and it's which features from physiological variables are useful for the analysis. Do you know about this kind of area or not? So that's another challenge. And the third one is in actionability. Once you're recording data in your virtual reality environment and you have access to bodily data, you want to review the sessions very, very easily, so you can take actions on what's happening to the users. So for these reasons, we have implemented the excitometer, which is an open source framework that allows us to integrate bodily signals in VR applications developed with Unity. And here there's an overview of the whole system's architectures. But it basically comprises three parts. It has the data collection section. Then you have feature extraction. And at the end, you have some modules about virtual reality integration. So you might notice that these submodules relate to the 3 challenges that we mentioned at the beginning. So we go one by one. So the first one in data collection is just we are collecting hard activity from the Polar H10 chest strap using the lab streaming layer protocol. So we developed some middleware applications that allow you to stream data from the wearable sensor to Unity through Android and Windows middleware. And the second type of data that we are collecting is head motion, and this one is very important because motion or movement affects heart activity. So we need to have a joint analysis of these variables when people is exploring in VR. And another important part here in this extension is that we are dealing now with multidimensional time series. And previously with heart activity, we were just working on unidimensional data. There are some features that are calculated. So besides heart rate, we have also another set of features that are usually common for cardiac analysis. And for the head motion, we provide real-time analysis of rotation, the velocity, the acceleration in both Euler angles and quaternions. And the whole real-time feature extraction can be easily configured via JSON file if the researchers need a specific window length or a specific period of feature extraction. There's a panel that allows to generate events to segment the experimental stages where you're doing the data collection. And it also, the plugin automatically takes screenshots from the scene. So in a post-session analysis, you can see which visual stimuli was generating specific body reactions. So in the last part with the integration, we have a package for Unity that can be easily adapted to any existing desktop VR project. So for the basic functionalities, it requires no coding. And we also have a panel for visualization that allows to do the post-session review. For all the data that's collected, it has a persistent structured data storage. So you can take the same data to do an offline analysis in the tools that you would use traditionally. And here is just a snapshot of how the built-in post-session visualization looks like. So basically, this is built in Unity, and if you compile your Unity environment, you should be able to see the screenshot, what the person was looking at, together with a comparison between participants in heart activity and movement features. As all the tools here in the workshop, then they are also publicly available here. I don't know if we have time for one question maybe, or we take the panel. Thank you.
Yeah, we can, any questions, or in fact, there's some of the tools that are coming after that have a bit of a taste also of data analysis. Sorry, and my camera's off also. Okay, and then so we can combine after the next session and perhaps discuss a bit more. I think that would be ideal, so we get back on track on time, and we talk about all these data capturing systems at the end of the next session. Does that sound good? Yeah. Okay. So okay, I'm gonna make Olivier needs to be co-host, and you can start presenting.
Okay. Okay, sorry, I was looking for the button to unmute me. Can you hear me?
Yes.
Okay, perfect. Thank you. And if I put full screen, oops, is it okay like this?
Mm-hmm.
Okay, thank you. So yeah, I'm Olivier Augereau, and I will present you some work that I've been doing with two master students about cognitive load analysis in virtual reality. So the first question is, why are we interested about analyzing cognitive load in VR? And I will present quickly some work that have been done in the European Center of Virtual Reality where I'm working. So this in this research center, we are about 40 people working mainly in computer science, but we have also some researchers in psychology. And we have many applications related to learning, training, and it can be about medicine, industry, military, heritage, and so on. So here I pick up just 3 examples among all things we are doing. So on the top one is about virtual audience. So we have some virtual students that are listening to the user. So it's for practicing like an oral presentation, and we can select the attitude of the audience. Under this, we have some application about medicine, like medical assistance. Here is in the International Space Station. And on the left, we have a wind turbine, and the user need to repair some part of the wind turbine, and we use VR for training. So basically, these 3 examples are about training. And in all this example, we can see that it could be interesting to know the cognitive load of the user. So the cognitive load is like how much the user is thinking or is engaged in the task he is doing. And if the task is too hard or too easy, for example, of course, it will have an impact on the cognitive load. So it can be a good way, if we have a tool, to monitor the cognitive load. So for analyzing from one side the user cognitive load, but also to compare, for example, different systems. So if we make some change in our VR application, and we can see if it has an impact on the user cognitive load. So for example, it makes the task easier. Also, we can compare users and see, for example, if the user is an expert or not. For example, if the user is an expert, his cognitive load will tend to be lower than a beginner. And the last thing that can be interesting if we have access to the user cognitive load is to create adaptive system. So for example, we can automatically adapt the difficulty of the system based on the user cognitive load. So if it's too hard or too easy, we can switch, we can adjust the difficulty of our training system. So yeah, the cognitive load is roughly the used amount of working memory. And there are, let's say, 2 main ways to measure the cognitive load. So it's quite similar to what Luis presented just before for the excitometer. So we have subjective measure. It will be questionnaires, so some famous one are NASA-TLX or PASS. And the drawback is that it takes time, and it can break the immersion if you do it outside of VR. But in our case, we do it in VR. We can show the questionnaire and fill it in VR. And bias, the bias is well known. And the other way to measure is to do objective measure. So also, as we saw just before, with physiological activity. But there is other way, for example, dual task. So dual task is, we ask the user to do a subtask at the same time, and we can measure the performance of the task. So for example, how many errors he's doing, or how long is the reaction time. So for example, we make some sound and we ask the user to press a button as soon as possible. So we can measure the reaction time, and this is directly correlated with the cognitive load. So we propose a platform, open source platform, and we give the link here, that can log all these measures through VR. And the idea is, we can do one, we can do the other, or we can do all measure at a time. And it's quite interesting to compare what we have. And I talked just before about one goal is to build adaptive system. For building adaptive system, however, it's impossible with subjective measure. We need to track, like in real time, the user physiological activity and try to estimate its cognitive load. And to do this, we need to use objective measure and to build, for example, a machine learning system that will be able to predict what we want. So to do this, we will need sensor. So that's a big drawback, by the way, for the objective measure. So we need sensor for measuring the physiological activity. So there are many ways. A common way to measure cognitive load could be by using the, I list here many sensors, EEG, so electroencephalography, electrodermal activities, how much you are sweating, BVP, so blood volume pressure, in temperature, and so on. And also by eye tracking. And I put eye tracking because in VR now recently we start to have some headsets that embed eye tracking. So it's a very interesting measure. With eye tracking, you can have the eye movement, and especially what we call saccade and fixations. You can have also the pupil diameters, and the pupil diameters is known to be related to emotion or to cognitive load. And you can also have the blink frequency, and it's also quite interesting measure. So in our system, for now, we just use this headset. It's the HP Reverb G2 Omniset. And it was interesting because they include inside with the headset SDK, and inside the SDK there is a machine learning model that can predict the cognitive load. So actually we built this system also because we wanted to see if this measure given by HP seems to be good or not, and if it's correlated or not with the other like subjective and objective measure we can do. Okay. So HP, they give actually the data set that they use to build their model, but they don't give the scene, the VR scene. And that's quite unfortunate. So we cannot reproduce their model and we cannot reproduce their experiment. So what we propose in our platform is to have everything. So to have in one hand the scene, the VR scene. I will quickly show you just after what kind of scene we included, and to include also the subjective and the objective measure. So by logging all the sensor embedded in the VR headset, and also by putting some questionnaires. So for now, there are two main tasks. One is just kind of a simple addition or computation. The user needs to point the answer on the screen and then press a button to validate his answer. So that's the normal task. And to do the dual task, we add also, as I said just before, some sound, and the user needs to press a button as soon as possible. So it helps us to track his reaction, the user's reaction time. And we also added another task when we have a bar here moving up and down, and the user needs to press a button when it's reached the green area. So all this task, of course, is to increase the user cognitive load and to record all sensor we have. Okay, so that's about it. And as a future work, we want, of course, to expand the compatibility. So for now, we use only one headset, and there are many, but there are not so many headsets on the market that embed sensor. So the other one we use a lot in our research center is the HTC Vive Pro Eye, because there is an eye tracker inside. So that would be nice to add this. And yeah, to add more tasks. So I show just, now it's just the beginning, but there are many other tasks that are famous for research in cognitive load. And also we will do some evaluation of the machine learning model of this HP headset I just showed. Okay, so that's it for me. And if you have any question, feel free to ask.
Thank you. Yeah, I wanted to ask because I say though, let's wait because there are more tools that I think have this analysis part, but if you want to do the panel now, I'm also okay. It just like it felt like we will have more later, but I think we can actually do the panel now with the session of the capture and analysis, right?
Okay.
So I would invite, can you stop sharing perhaps?
Yeah, sure. Let me, no.
So perhaps if we can have Dieter, Sean, Aria, and Luis, and anyone really who wants to ask questions or participate will be welcome. Right, so I guess one of the questions is, how can we standardize or come together into not having many versions of sort of similar things? Or, I mean, each one of them has very different approaches in a way, but also it feels like if you want to use all of them, it feels it's going to get very crowded, right? How do you see that going? Perhaps Sean, can you start?
Yeah, sure. I mean, I honestly have no idea. I don't know. It's just, I think it's going to be hard because this is still such a new technology. There are still so many different things that people want to do with it. And I think it's kind of natural that for at least a while, there are going to be lots of different kinds of tools that target different kinds of things and help with building different kinds of applications, right? I think if you look at a certain distance, many of them seem similar, or maybe seem like they're tackling similar things. But it's like the devil's in the details, right? Like you start to build things and you realize like, oh, I actually need something kind of pretty specific here. And once you start narrowing kind of your requirements, you see that actually there's maybe one tool out there that fits, or probably zero, actually. So, you know, hopefully, you know, some of the, like, I just think there are going to be more and more tools. Hopefully they can kind of start to work together, you know, integrate with each other, find ways to sort of interoperate with each other, and things will start to coalesce. But I don't know, coming up with standards like in advance, I think is going to be pretty difficult.
Yeah, I think a bit we need like an OpenCV moment, right? OpenCV started collecting all these tools into this library. And then even today, many people who do computer vision will use OpenCV. So that would be a goal, I think. I don't know, Dieter, do you have some comments on this?
Well, one comment would be that there's always the syntax and then the semantics of the data. So the syntax problem, I believe, can be addressed. Like, for example, everybody's using JSON for sort of lightweight representations now. That's fairly universal. Other protocol, like network protocols like RTP or the MQTT that I mentioned would also be instances of sort of syntactic standards. But on the semantics level, it's harder because then you need something. You mentioned OpenCV. I was reminded of, let's say, you now have a standard such as OpenVR, which standardizes some functionality. and then various implementations of that can happen. But if you go out to this multimodal and also the domains like artificial intelligence, inference, and so on that were discussed today, this is such a broad area that the standardizing the semantics of that seems futile. that will have to happen via some best in class, which then sets an example and everybody's sort of riding along.
So what you would recommend to other people who are starting to build tools or using tools moving forward, right? Considering this is a moment of a very incipient moment, right? We have, I mean, Sean, your tool is fantastic, and Dieter also, and then you see smaller tools that are also very oriented to particular things, like the excitometer, for example, right? Which is for physio signals, or some very. What is your recommendation for people who are moving into this space, either as users or as builders?
Yeah, I don't know. I mean, I don't know. Be careful. It's a lot of work. I think one thing I would say is, like, one thing that we've kind of been learning as we build up Psi, and I mean, I think first of all, when you're getting into it, you kind of obviously take a step back and like take a look at the lay of the land, and obviously try to make sure you're not reinventing a wheel that someone's already invented. But again, probably there's some unique angle or some kind of unique use that you're targeting that is different from what is out there, which is why you're building the tool in the first place. But then I think something we've been learning is, like, again, we built this infrastructure and we use it a lot in our own research. And then, like, okay, this could be great to share. We want to share it with other people. We think it's useful. We're not salesmen. We're not going to like go and force it on anyone, but we want to kind of just talk about it at conferences and things. And I think what we found is one of the best ways to kind of get people to consider it or think about using it is kind of showing how it can integrate with other ecosystems, or just having examples of where, if someone's coming from some other ecosystem and they kind of have some interest in your tool, how would they go about using it? So the example, like my background is in mostly human robot interaction, and I've done a lot of research in social robotics. And so in early days, like I was talking about this, especially at robotics conferences, and people over there are mostly using what's called an ecosystem called ROS, Robot Operating System, to do a lot of their robotics work. And so they would always say, like, okay, well, how is this different from ROS? Or I want to use it, but I only know ROS. Like, how do I jump into your tool? And so putting like just examples and including integrations and having kind of sort of walkthroughs that are not general, but are like, okay, if you know a lot about ROS or whatever, you're going to think about things this way. And if you want to use this tool, here's kind of a translation or kind of how you can think about building things that either use both systems or kind of transition from one to the other. So I think that was really important, is just finding connections and overlap between the other kind of tools and ecosystems that are out there.
Okay, sounds good. Okay, perhaps at the end of the whole workshop, we will come back a little bit into how we try to bring things together a bit more. But so let's continue now with Chu Jing.
Hi everyone. So I was thinking another challenge will be the data, because we are talking about the people, the users. If we don't have like their age, their like the health information, actually it's really hard to compare the data among the different projects. So yeah, it's a huge challenge, and also opportunity for most of us.
Indeed.
Okay, so I was just want to share a little bit. I'm trying to use some computer to replace some humans. So here I'm going to talk about a project I was running last year. So compare the human vision with computer vision, and it's a readability study in the virtual reality environment. So next page. Okay, so I want to give you a little bit background about this project. So since 2018, we start to use the VR to train the Missouri DOT Department of Transportation work zone inspectors. So to ensure the compliancy in the work zone and improve the safety for the worker and also for the travel public. So here's a short video clip of the VR simulation. So to set up the work zone scenarios, we use a lot of the traffic signs. So both symbolic and the text-based signs. So there are some trade-offs between the symbol and the text-based sign. We found that many DOT, the trainees report that the text-based sign were not able to read until very close. So clearly, we have a readability issue in our program. So in order to improve the readability, we have tried changing a lot of settings in both hardware and software. I have to say that if you want to get to the best resolution, best solution is to get a new the VR headset with a higher resolution. So definitely that one will help to make those signs more readable. But however, when there is no headsets available, so we have to try a lot of changes. So for example, we were looking at some settings and compared the result from the texture resolution, the size of model, even the vehicle speed, to the texture types. So many trade-offs, and we were changing one or two factors. And from the perspective of the experiment design, you can see it's a huge problem of all different kind of the small factors. I don't think there are very big ones. So if you're creating the VR simulation, you probably will deal with it, but it's hard to when you're trying to deal with all of the factors together. So here we just look at another way how we are going to evaluate the method and tell us which one is the better solution. So I know that mainly people do the readability evaluation just by recruiting human participant. So they have some human participant prepare the protocol and do that, get some feedback. Another way is where we're testing is about using the computer vision and give us the readability measures. And here, just a quick summary about the different evaluation method. So most of the time, I will just do the in-house testing. So we have a limited sample size, and we are biased because we know too much about our experiment and our scenarios. And if we are going to decide to open to the public, so we have to prepare the research protocol and also get IRB approval, recruiting, and scheduling. It's a very time-consuming and costs a lot of resource. And another solution we test is by using the cloud computer vision service because its quality is much better than the some offline, the open source libraries. And the time is relatively short. You can finish the evaluation in 1 or 2 days. I know there's some cost because we are using the online cloud service. Actually, it has to some kind of fee, but compared to the human experiment, I think it's a very reasonable. The fourth one is easy to use, and also you have a lot of choice from the Google, Amazon to Microsoft. They all have the very good online tutorial to show you that. So I'm here not going to have enough time to show how to do that, but by following the tutorial, I think we just mentioned that I think everyone will be easily to use it. And here we just want to show the result. So we do both evaluation, involve the human and just using the computer version. First of all, for our human participant, we also get the IRB approval. So we have a 10 human participant. They are outside member, so they didn't know too much about the experiment. And we tried three different text-based sign, and we do the comparison. We found that we have very similar the farthest reading distance So here you can see that I'm pretty much the cloud-based, the computer vision actually did quite a good job to has a very similar result with the human. And more importantly, we find the conclusion is that both evaluation methods show that those methods are improvement, but not significant. So using different methods, and we can draw the same conclusion. So we just think this one actually can facilitate our future development in the VR environment, especially reliability is an issue for your program. Okay, any question?
I think this was an interesting project that brings a bit this idea of applications being more wide than we think sometimes. So I liked it because, you know, sometimes we focus very much on the tools and we need to also think who's going to use it and think of interesting uses also to improve the tools. If anyone has more comments or questions. Okay, so we can move to the next presenter, Jonas. Or Jonas.
Yes, thanks.
How is it? Is Jonas?
It's Jonas, German. So I think you can see my screen.
Yes.
Okay, so hello, my name is Jonas Deuchler. I'm from Karlsruhe in Germany, and I'm here to present a feature or technique that we are planning to integrate in our open source toolkit. It's called asymmetric normalization. And yes. So yeah, with the increase of the popularity of social VR platforms, we are also diving deeper into the research into virtual interactions. And so we rely a lot on polyadic studies with more than one participant. And in a social interaction between two people, let's say participant A and participant B, as seen here, each participant brings individual characteristics to the interaction that influence the communication between both of them. For example, that could be the appearance of someone, the height, the clothes, or the gestures they make. And this can lead to possible biases and possibly overshadow the observed variables. And so in the best case, we would want to control for these unwanted influences, individual influences, based on the observed hypothesis. Now we could just embody everybody into the same generic avatar to keep a normalized version, but that would then the embodiment would be very bad. So we employ a technique called we call asymmetric normalization that and that refers to the decoupling of self-perception from the perception of other users in a shared virtual environment in order to present everybody with a normalized version of each other. And this idea of the asymmetric distortion is similar to the research history on subjective use or the transformed social interaction. In our case, we want to use it to normalize the individual conversations. And the targets are first to reduce possible bias, and by this to increase replicability and external validity. And at a second, also to gather new information on social interaction that cannot be observed easily in the real world. How so, and to which areas of social interactions this can be applied to, I'm going to explain in the following. So first of all, we have the appearance. Like I said in the beginning, there are individual factors like the height, for example. In this case, if your conversation partner is much taller, that could be perceived more dominant and then so influence how you behave towards them or how one of your participants behaves. And so it would be best if we could normalize, scale other participants from a participant's perspective to an average human height or average height of a target group. And this goes for both sides. Also, participant B would see everybody according to their average human height. Simultaneously, it is important to keep everybody embodied according to their true height. in order to maximize the embodiment. And we refer to this asymmetric distortion by appearance normalization or height normalization. And this could be applied to other appearance-related factors like skin color, clothing, or tattoos, everything that could influence the behavior of interlocutor. And next to appearance, we could also apply this principle to the location of participants. In a normal conversation between two people, both participants would close in on each other, walk towards each other, and everybody has a preferred interpersonal distance. In this example, participant A is walking towards participant B because they are conversing with each other. And also participant B would want to move towards participant A. And in the real world, both participants have to agree on a common distance. And the thing is, in a virtual world, we have the possibility to have everybody move according to their own preferences by normalizing other participants. And that means hiding their movement from the other person to present everybody with the same distance and make everybody take their own individual preferred distance. Here we can see participant B would want to take a higher distance towards his partner compared to participant A. And if we wouldn't normalize this, this could have adverse effects for participant B if participant A comes too close to him, for example. And a third area where we observe observe this technique is nonverbal communication. You can imagine a remote study and people joining with different cultural backgrounds. This might lead to incomprehensible gestures for some participants. And with asymmetric normalization, we could normalize these nonverbal behavior to the individual's culture or to a target group of the study. Another use case would be, for example, participants joining a remote study with different VR setups, different VR technology. And so we have devices with a lot of tracking functionality like face tracking, full body tracking, together with participants joining with a Google Cardboard, for example, just having head tracking, no hands. And this is what we observed in a small preliminary study in a proof of concept of this technique. We asked ourselves if people behave differently depending on the tracking fidelity of the interlocutor. Specifically, do they have different preferred interpersonal distances? And so we had two groups, one against a high tracking fidelity participant and one against the low tracking fidelity participant. And we found out that after 2 minutes of casual conversations, people opposing other participant with very high tracking fidelity took a distance of 189 meters against the group who talked with a low tracking fidelity avatar took a closer distance with 168, a significant difference. And interestingly, this can only be observed by the use of this location normalization principle. And yeah, what's the outlook for this? We are planning to do further research into this technique. When can it be applied? What are its use cases? And its possibly adverse effects. Like, for example, some of these things we want to normalize are also means of communication. For example, the distance you take to someone and what influence has this, and what other areas can this be applied to? For example, the speech of the participants. And a really important point that I want to mention is that we plan to integrate this feature into our open source toolkit, the so-called virtual reality scientific toolkit. This is a Unity 3D package that's making it easier for scientists to set up their own studies. It has functions to capture data more easily, to export them to JSON and to replay data right now. And we want to extend this for the multiplayer functionality to conclude multiplayer studies and also include this normalization feature that we are working on. It is available under MIT license, and the feature will be probably available in the next 2 or 3 months. So any questions? And thanks for the attention.
Yeah, this is very nice. I wonder how it works when you're trying to interact with an object in the scene, right? Like grab something and you're of different size. Because one thing is the size you feel you are, and the other is what your avatar actually is for.
Yeah, there are some limitations. Also, participants might talk about this. That's also a problem. We have to restrict some the communication between them, or if they're holding objects, like you say. And also we have to, if we normalize the position, we also have to correct the eye angles, for example. So if we use full body tracking we have to use advanced leg IK, because the legs are moving different if you're standing still and if you're moving. And yeah, it's quite interesting.
Sounds good. Okay, so we're gonna move forward. We have now the authoring and access session. We're gonna start with the Babia XR and David. Okay, I need to make you co-host. Okay.
Hello.
Okay, you should be able now to take over.
You are seeing my screen and you can hear me, right?
Yes.
Perfect. So hello, everyone. First of all, thank you so much to Organiser and chairs for making this workshop possible. I'm David Moreno, and I'm going to present you Babia XR, virtual reality data visualizations for the web. And what is better to start than showing directly a live demo? Let me change. Oops. So this is the first demo. It's just the browser showing us scenes with a data visualization with some interaction with the cursor and with the keyboard. And well, as I said, this works in a browser. So as probably you notice, this is based on WebXR. And this scene is also compatible with VR glasses, or any modern device with a modern browser can show this scene. And it's better to see these scenes with the VR glasses because you have the interaction with the VR. Well, maybe it doesn't seem amazing, but what if I tell you that this is just the code for generating this scene? And yes, it's not technically code, it's just HTML. This is possible using two things, a frame and Babia components. So if we add a few more lines in HTML, we can create scenes like this one, a complete launch, like a museum, but showing your data and with the possibility with interacting with all the visualization, with the cursor and with the controller of your VR glasses. And well, you can see in this scene different visualization, and this is one of the most important that Babia has, is this one with the green base that shows a city. I will show more information about it in the presentation. It's just the code city visualization, and I usually use the Oculus Quest 2 to try this kind of scenes. Okay, and again, this is the code of the HTML code of the demo. So going back to the presentation, I want to say that this is full of QR codes and links to examples and documentation. But the most important one is the link to the main page of Babia. That it includes all information, useful information about the uses of Babia, the installation, the documentation, and examples. This is still work in progress, so we appreciate the feedback. Again, this is the first link to the first example that I showed. This is the link to the launch example. So Babia relies on iframe. iframe is a web framework for building 3D, AR, and VR experiences with HTML and the entity component system that has. I'm not going to stop here about technical things about iframe, but iframe is developed on top of 3GS, and again, with just at these few lines of HTML, we can create scenes like this one. All the logic is of the components is developed in JavaScript, and you have information in the main page of iframe on how to start with this framework or how to develop components like us. Okay. So Babia XR, as I said, is a set of iframe components for data visualization, but it includes components that are not just visual. It includes components for query data, filtering data, and visualizing data. So the first component in the stack are the components for query data. We have currently 3 types of components that retrieve data, one for retrieve data from a JSON file, from an Elasticsearch search engine or database, or using the GitHub public API. More are going to be included soon. And of course, we are open to new ideas. We have a component that filter data. I'm not going to stop here because of the time. And this is also another component for creating trees from a field of a list. This is used just for a specific visualization that shows a tree structure. In this case, the city visualization that I already showed in the last demo. But I'm going to get deeper later. And the final components of the stacks are the components for visualizing the data. We have included so far the next ones, but the last one is the code city component for visualizing codes as city, the most important one. But before starting with this last component for visualizing cities, on the sample page of Bavia, that is included again in the main page of Bavia, there are visual examples of each component described in this presentation, if you want to take a look. And I want to leave this link here, where all the information and the details about the component, definition, attributes, and user guides. The link is to the README, where there are a small example and the API of each component. And the other one is the component user guide with a step-by-step guide for using the components stack. And focusing on the code city visualization or the city visualization, the idea of integrating this visualization of the city comes from the scientific literature. Since at BioXR, we carry out research tasks, as we are doing now. So the city metaphor visualization is nothing more than representing metrics in geographical aspect of the city. In this case, the organization of the buildings by their neighborhoods and their height and area, the depth and the width of each building, and the color of the building. The main idea comes from the code city tool, which is intended to visualize Java code metrics in this visualization. So the metrics available for the visualization are basically the neighborhoods and the district structure, which ends up being a tree structure. And as a numerical metrics, the height, the area, and the color of the buildings. And the colors change according to intensity in a color map from blue to red. So combining these metrics, we can create scenes like this one. This is an example, a quick full example of how to use this visualization with Bavia. First, we have to add the query that brings some data, the query for bringing some data, with the data style that is shown in the screen, a simple list, this one. Then we have to add a tree building that takes the data from the query, searches in the field that we have defined, and parses it to create a tree from there. In this case, we can see that this is a path, and we parse it from the slash, and we have a tree of files or folder. It's more like, we use it for analyzing repositories, for instance. Finally, our city component, which is the case of Viva votes, selecting which tree we want to represent, this one. You can see that you have seen before that I said votes and not city, right? That is because we have 2 algorithms for the structure of the neighborhoods and buildings. The city one that we call it a city is a tree map bounded in a defined square, and the vote one has the freedom that the city grows following a spiral starting at the central point. If you want more information or have any question, please tell us. Well, this visualization is completely configurable. I'm not going to stop here on these details, but in the documentation, there are all the details to customize the city. And finally, at Bavia, we have a set of tools, apart from the components, to analyze software code repository in this type of visualization, the city or the votes. The tree structure of the file, structure of the code, and the building metrics can be from lines of code, number of functions, tokens, complexity. We focus on analyzing software development metrics. This is a diagram of how we do the pipeline to create this type of city, but I insist that in the documentation, there is a guide to create this code visualization step by step. Finally, this is a code city sample for the JetUML software project. And as a preliminary result of Bavia, we have presented a paper at the BISOF conference running a controlled experiment that compares the version of Code City, both in use with virtual reality glasses and on screen. And in summary, we consider that the results of our experiments so that the code sitting VR is comparable to code sitting on screen with respect to the accuracy of the results, and much better with respect to efficiency. And as accuracy steps, we are working now on the time evolution city. I mean, it's just so how your city, imagine that this is one of your repositories or GitHub or GitLab repository, how it's evolving along its releases, for instance. This is an example of the Jet UML city evolving along its releases. And also it's better to see this example with the VR glasses, because you have all the interaction with this navigation bar and so on. And in Bavia, we have deployed an WebRTC server, and therefore we can show live demos of the multi-user mode. So we have multi-user, the multi-user mode, and this is being thanks to the networked component that allows several users to enter and scene and share the graphics created with Bavia, as well as the changes that can make to them. And this is an example of how an user is evolved and how it looks in two browsers in the same scenes. Okay, this is the link. And of course, we have these two examples that are always up. So if you want to join these two scenes with some other people, you will be able to see them and to talk to them and so on. And now we are working on integrating this with Mozilla Hubs. To finish, I want to show some other components that are under development right now. The terrain visualization for plotting terrains that represent data. And the lookup component that forced an entity to follow another entity. I will say that it's like an object in the space. In terms of position or rotation, follows another entity in terms of position or rotation. And of course, any other idea is more than welcome.
Perfect.
Sorry.
Yeah, I think we were on time.
Yes.
Okay. So if there are any questions right now, or we can take later. Yes. I think this is.
I was going to finish.
Yeah. Okay.
Thank you.
Okay. Good.
If you have any question, here's my email, or if you want to open an issue, it's more than
perfect.
More than
I mean, it's great to think of ways we can be more accessible as we are moving to the consumer, right? Or if we want to run studies, it makes lives easier if you don't send them an executable and right? Like it's easier this way, perhaps. A part of the data visualization. So we're gonna move. John Murray will present the next work, reality flow.
Great, thank you. Let me begin sharing here. And, all right, I need to switch there. Okay, is that showing all right? Great. Yes. Thank you, everybody. So I'm going to talk to you about something that everyone here seems to care about, which is how do we solve the trick question of making something that's reusable, maintainable, and useful for research, which isn't the primary motivation for a lot of the tools and hardware that we're working with. So this project is ongoing, but I'm happy to report some of the early results and the fact that we have an initial release on GitHub. So it specifically focuses on immersive authoring. So instead of working inside of an IDE like Unity or Unreal, where you have a computer, immersive authoring is making changes inside of VR or AR that would in turn have these features available to users or to evaluate as you're authoring them. A lot of these tools are primarily targeted towards novices. Very few are targeted towards experts right now, because experts will likely use something like Unreal or Unity to complete the work, and they'll have a much broader range of options in terms of connecting with cloud libraries. I'm happy to see a lot of the work being done on that in this workshop in terms of how do you make it easier to use something like Node-RED to hook stuff up to IoT type things. So I looked particularly at available tools that were published and that could be used in a study that are currently commercial. And I'll go over some of those. And what I found is a lot of these are very bad for research. Either you can't make changes to the tool itself for an experimental variable, or there are licensing restrictions around how your users can use or interact with that software. Particularly Facebook Horizons is a good example of that, where they basically won't let you conduct research on Facebook Horizons without cooperating first with Facebook on it, which is more overhead than a lot of us researchers have time or energy for. And we also can't necessarily introduce novel features. So none of these platforms allow you to add additional nodes or additional debugging tools. They're all essentially fixed as they're published or updated at the whims of the company that runs them. So the motivation for creating a new immersive authoring tool, when there are several that are currently available in the literature, was to teach computational literacy and to increase motivation towards STEM disciplines. And seeing the success of tools like Scratch and Blockly for introducing programming concepts through a more novice-friendly interface. The tool was created around 2018 for that purpose and was developed over the past 3 years by UCF senior design students. We also looked very closely at the options I'm going to go over in terms of how well we could run a study to compare them. And a lot of them have such different choices in terms of the features and the interfaces that you can't compare them side by side without really losing sight of any of the variables that were under consideration. So even ones that both use a data flow paradigm make very different decisions around how that data flow process is visualized, enacted, what are the set of nodes, how are the nodes manipulated. So it's very hard to control for these things within a single platform system. And they're also all designed to produce work for the most part within the host environment. So unlike Unity and Unreal, you're unable to export a content scene from one of these environments and then run it on a different one. So content developed on Neos or Horizons cannot be in turn integrated into an independent app and then hosted on the Oculus App Store. So to this extent, these are almost toy sandbox environments designed for user-generated content to increase the value of the platform rather than as tools for computing, and something which we could promote some of the things we all enjoy with tools like Jupyter Notebooks, which really furthered the art of scientific computing. So specifically, I was interested in evaluating which paradigm was most useful for novices in terms of designing content inside of an immersive environment, whether it was a block-based paradigm, such as Scratch, or a data flow paradigm, such as described earlier with Node-RED. And I'm also interested at targeting early undergrads as well as high schoolers in terms of their first encounter with authoring through computing, as a lot of programming is really off-putting by manipulating strings or by encountering maybe robotics. Not every student is motivated by some of the traditional introductory tasks, such as those presented in Scratch. So this project has been under active development by senior undergrad CS senior design students. And this presents its own problems in terms of how do you transition from one team to the next? How do you maintain the project? How do you make sure that the new team can come up to speed quickly? And some of these are shared with any open source project that has a lack of funding. So we'll talk a little bit more about that, but primarily we'll present some of the features and motivations behind the current work. So there are 4 main works I want to talk about. Zoe, for instance, uses a action trigger paradigm. So it provides the ability to bring in models from Sketchfab and be able to add triggers or conditions like gravity to them. And it uses a form-based method here. So users can use kind of a tilt brush style interface with a palette on the left controller and then directly add these interactions to objects within the environment. Neos VR has its own integrated logics environment, which is a data flow programming environment where you have a palette of possible nodes that function as either inputs, outputs, or transformation of the data from inputs to outputs. It's a 3D paradigm, so you actually manipulate nodes in 3D space, and that may or may not result in a spaghetti mess depending upon the complexity of the code, and also result in some difficulties around finding related functions when you're trying to debug something. Facebook Horizons has a Scratch-based tool that basically develops things like events. They trigger different actions. They also start with fairly sophisticated controller-based interaction mechanism. And this is the best example of a Scratch-like environment where you have a menu of possible events to respond to, and you don't have to go at the low level of C# or the Unity API to interact with them. So it's much more accessible to novices when they want to take their knowledge from Scratch into VR. And finally, a really popular app, Rec Room, has its own node-based program called Circuits, which allows you to create behaviors that respond to events and visualize their inputs and outputs as well. Very similar to Neos VR. A particular note about Rec Room is it actually has a mobile client, so you can actually change and author things in the mobile app as well as in VR, and they use the same interface for both. There's not a mobile specific interface for Rec Room. So for Reality Flow, we designed a Unity plugin that connects to a server. So as you make changes inside of the play mode of Unity, either on a client or inside of the editor, those changes are broadcast via WebSockets to the other clients and persisted, more importantly. So the ability to be able to make changes and see a history of changes is available, especially for research purposes. It uses both a custom WebSocket format as well as a GraphQL API, so you can make changes to the clients without having to redo the entire server. GraphQL gives us a lot more flexibility in adding additional modules and features to the database without changing the server code extensively. We were focusing more on how do you keep the low latency for like dragging a node around and being able to see that on another client screen, but not necessarily making every one of those updates persist to the database, but also having the ability to maybe export or import data from this application from Reality Flow, especially with the idea that a lot of these other applications didn't have that feature to export the data or to really discuss what does a content format look like that could be shared among multiple platforms and possibly further our way of understanding content development and what are the right paradigms for content in authoring tools in general. We do use Node Graph Processor, which is a Unity plugin as the core, but we add an interface for VR into it and a way to persist the data to a database. And you could see more of that on the GitHub repository. I'm just going to show a couple of brief examples, but of interface interactions in the next slide. But we decided on a whiteboard-based approach because we observed that some of the 3D interactions with graphs and nodes in other data flow interfaces often made so it's hard to see the relationships. But if everything is potentially constrained to a single palette or a single whiteboard, it's easier to organize that through auto layout mechanisms and also to filter it as well. But likely some alternative might be worth evaluating as well once this is fully fleshed out. We're also able to persist any changes to the assets, transformations, adding behaviors and changing colors to the database. And so it's not actually making changes that are just local to the single client. And here's an example of the current node interactions where you can add names to them and connect them. And you do that through a ray-based mechanism on a whiteboard. And you can create multiple graphs that are associated with different objects through parameters. Again, a lot of the details about how Node Graph Processor works are useful if you want to look at the code base. Then there's also this notion of connecting the nodes together so that the input and outputs are aligned, and every client can see these updates as an author do it. So you can collaboratively work together to change the same graph, even though originally it wasn't designed for a network-based authoring scenario. And this particular example is adding a trigger so that when this model intersects with that volume, it changes a color. Pretty simple example. And then this is an example of the mobile interface that uses the same data backend, but has a different interface so that mobile users, potentially in a classroom where you don't have one headset per student, can still participate in the authoring. And I find that the case because the current program I'm running at a local high school, hardware constraints are such that I can't have one headset per student. So a lot of them have mobile phones and can potentially contribute and get engaged. So in terms of the future, we'd like to create a library to test these hypotheses around block-based programming versus data flow programming and to have the same library of interactions for both so that you're able to constrain the experiment so that they have the same vocabulary and to evaluate against it a target demographic and potentially see how immersive authoring could motivate the next generation of STEM practitioners or to get more people into computational literacy and programming who may not otherwise see themselves as someone sitting in front of a keyboard and manipulating programs in a traditional sense. We definitely want to improve the code base and are looking for contributors because obviously this project is of value to the community, and I suspect the only way to maintain it and to really further its goals are to incorporate contributions from others working towards these same goals. Thank you.
Great, thank you so much. Always a challenge to create VR from inside VR. Still, we don't have that. We need to go to the PC. So yeah, I like to see these approaches also very challenging to have all the students, right? How long have you been
turnover
running this open source project for?
So it's been mostly closed source. This actually is the first public release of the code. And it's been in active development since about 2018. So there's been 3 previous groups, and I just had a new group of 5 students that are now going to work on it over this semester and the fall semester. And each of them are building new features, but clearly they also have challenges around maintaining it and not saying, oh, I want to do shiny thing over here and then fork the code base or make a different database decision or something like that.
Okay, yeah. Well, it's great also that they get to learn with the real practice. So we're gonna move to the last presenter of this session. Alex?
Yeah.
With the spatial markers?
Yeah. One sec.
Did I make you co-host? Yeah.
I'm having to let it. Computer doesn't appear to want to let me share it though. Okay. Can you guys see my screen?
Mm-hmm.
Okay, great. I'm Alex. I help make a spatial marker system. And so in augmented reality, you have the interaction between both physical and virtual objects. And if you have multiple people all in the same augmented reality space, in the same physical space as well, all the physical objects will show up in the same location, but not all the virtual objects are going to be in the same location unless you add some constraints to that. And in a lot of cases, you would prefer that the virtual objects are in the same physical location for everyone. And that's what the system helps to solve. There are some other tools that do this, specifically Azure Spatial Anchors and Google's AR Cloud Anchors. The issue that the lab I'm in has already had with these in the past is the lack of customization they allow. We've wanted to do things like measuring latency and like what level of latency is noticeable from the client's perspective, as well as how much inaccuracy in positional location is available. And a lot of these other larger products don't really allow that level of customization. They also tend to rely on going to and from the cloud and to and from external servers. So when we first started using Azure's spatial anchor system, there was a lot of issues where they would keep updating their platform, and it would require us to keep updating our code base to fit along with their platform. So it made it hard to run the experiments that we wanted to run. To stop, and like as I was saying, we also wanted to measure latency, and so we had, and Azure and Google's systems don't really let you control your network stack. And we had some people that really were interested in, is it worth it to go all the way to the cloud for a lot of the computing versus just going from one edge device to another edge device? So what our system actually does is it aims to sync several coordinate systems together, which is done through several linear transformations. And the first step for any of this is you have several different coordinate systems. You need to find a shared point to use as the origin for your global coordinate system. And then from that, you can construct a vector space that you can convert to and from in order to send and receive locations of objects so that each device will see the same virtual objects in the same location. And so the goal that we had when we were designing this system was to make it so that each part of this process was entirely separable from the other parts, so that you could control down to whatever level you wanted to the network stack without having to worry about any of the alignment issues, or you can control down to whatever level you wanted the alignment without having to worry about any of the unity logic to move the items around. And so it's the way the system is constructed is in several parts. And so we're giving each part has a basic system that works as it is. And then you want the developer who's using it to be able to modify it to fit their needs better. So maybe if in some systems, you don't actually care if the accuracy of the alignment is very high, you can use a slightly easier and less intrusive method of aligning the systems than the default method of placing a headset, all of the headsets or devices in the same physical location and using that as the global origin point. And on top of that, so those are all future steps, right? It's really easy to build off this base platform by making modifications to any of the subcomponents. So right now, a lot of the components don't actually support all of the features that would be ideal, but there's so many features that would be ideal that allowing the developer to figure out what features actually matter to them and work on implementing those rather than being forced to use all of the features that some other system is out there was the idea of the product, this project. The two big ones that I hope to continue working on is the way the system is set up now. All of the headsets or devices have to share some level of scale. So if you move one unit forward in one headset, you should be moving one unit in some direction on another headset. And that's not entirely true between all headsets. So solving that problem is something that I hope to continue to work on, as well as the way it's set up now. We only compute two vectors for the vector space, or for the basis of the vector space, and you need three. And so our default vector, default y-axis is just straight up from the headset, which does limit some devices that don't necessarily have accelerometers to know which way is up or which way they're moving. That makes that problem a lot harder. And so we'd have to add that in, as well as adding things in like another person in our lab is working on a different networking stack that we would like to incorporate in, make it a little bit more easy to expand on. Yeah, that's all I have.
Okay. Sounds good. I think we can move on to the, somebody has questions, sorry. Regarding the spatial anchors. I'm just wondering, how much of these do you expect to be already there when you use Vuforia, right? Or some of the existing platforms? And
yeah, a lot of these things have been implemented in the existing platforms, but they don't let you, from my understanding, Vuforia requires you to use visual markers. And so it scans the room and does that. And oftentimes that's a really great solution. But in some situations that's not necessary. It can be overkill. It can be very computationally complex. And we were running into issues with Vuforia about it not letting us take away that aspect of it. And because it's not this module design, you either had to use it all or none. And that was not something that we would like to use parts of it, but not all of it. And so, yeah.
Sounds good. Okay, I think we can, oh no, we cannot take a break. I think just the breaks are a bit of buffer in reality. Joan, are you ready for the presentation?
Sure.
Okay.
A complete change of topic.
Yeah, we're moving into avatar tools. And as you know, avatars are this cute thing that becomes really hard. So let's see what we do here. Okay, thank you.
Okay, so let's go. I'll try to explain to you why I'm looking into physics-based animation. I come from a virtual reality background. Can you see my screen? Yeah?
Yes.
So
correct.
Why physics-based animation? So normally when you animate a character, you use kinematic animation controllers. This is the machine state that is behind some of the characters in Half-Life Alyx, a big VR game, or you use inverse kinematics, or if you want to do something fashion, you do motion matching, which gives very smooth movements, but only works well for navigation. You cannot kind of grab objects and move in the animation database easily. Okay, so there's some challenge, because if you look at how people actually so when you put this in a video game or in a virtual reality, the kind of movements you see, very big transitions. This is actually a parody, but you get the effect. If you've played video games, you get a lot of this thing, which doesn't feel really natural. It's kind of tricky. And in video games, the kind of characters that you have, they have some interaction. This is a super game, super hot, works really well, but you don't get the kind of rich interaction that you get with people when you are in a shared social space. Okay, so when you look at how people actually interact in the real world, something that happens, for example, is that there is lots of imitation. So particularly when you tend to understand each other or agree with each other, you have this thing that kind of you synchronize the behavior with each other. And this is not just like an implicit thing that maybe improves a social interaction. For example, this is from a recent paper of this year. It shows that if you play the mirror game with all people, it actually improves cognitive performance. So it kind of also has therapeutic applications. So maybe we could do this also with virtual characters. That would be great. It would give us smoother interaction, etc. So something that you can do is that this is from an old study that we did. We studied these kind of movements. We captured everything with full body mocap with our statistics. It was kind of a psychology study. But then if you want to create these characters that kind of do some mimicry, but also have some initiative with you, you're kind of stuck. And with this kind of old, let's say, well-established methods with state machines and pre-existing animations, it's kind of tricky. If you want to create a perfect mirror of yourself, it works really well and it makes you feel more in VR. But if you want to create someone else that reacts to you, but is not exactly like you, it's not that easy. Okay, so I was thinking, okay, how can we do this, etc. So something that is different from VR, but that is had been going along in parallel, is physics-based animation. So in a video game or in a virtual reality, obviously physics is a simulation, so you can manipulate it however you want to. Okay, and something that happened 5 years ago, more or less, the state of physics-based character animation was this. Basically, you told the character, hey, I want to walk forward. And there was a deep learning system that learned to walk, but it learned to walk in this strange way. This is not usable. It's weird. And if you put this in VR, people just are scared because it's really strange. Okay. But what happened is that there was this genius PhD student who put out this method. And let me just show you the movement. So this is a physics-based character animation. It is trained with one air kick, but you can see that the movement is always continuous, smooth. And if you move the target, it retargets the movement, and it's always fantastic. It's smooth and perfect. So then I said, oh, maybe we could do this and put it in VR. So this is one example of something that is in Marathon now. So the red thing that you see is a kinematic character with a controller, and the blue one is actually a physics character. So you will see when it turns, for example, that it doesn't do this perfect turning, but it kind of, whoop, it kind of trips because it has inertia and it has this kind of thing, which makes it a bit more smooth. Okay, so this is what we are trying to do with Marathon, to simplify the adoption of physics-based character animation for virtual reality or for video games, okay? So this is, physics-based animation has been going on for very fast. So this was 5 years ago. After Deep Mimics appeared, that paper that I showed you, then everyone started to animate characters. And then this is a recent paper where basically they train one simple physics character to imitate like a whole database of motion capture data. So it kind of knows how to jump, swim, crawl, etc. Okay. Here I have to say there are two different strategies in physics-based character animation. One is I have a kinematic controller and then the physics controller only learns to imitate, okay? And then the other is I take away all the kinematic controller part and the entire physics controller is the one that learns the task. And then you have to put targets like when I showed you the air kick, you need to put, okay, put the kick here, but then you can make it learn with targets that are more abstract, that are not so much like move forward, but you could, for example, train it to keep a distance from you all the time. So it respects, for example, interpersonal distances, which is a pain in the ass when you have these virtual characters that bump into you and you feel like, shit, this is horrible. So it could generate these movements by itself. And if you want to do it by hand with state machines and do like every possible configuration of a user and a virtual character, it becomes very rapidly a nightmare, okay? This is the progress. So I showed you the Deep Mimic paper that was in 2018. The one I will show you is from last year. I think it's the best I've seen so far in this regard, where it learns from abstract patterns. So you give it only one reference animation, okay, like the one I showed you, and you can learn several parameters. So here they train it to generate different angles and even different kick positions. So what is still not known is how much can you push this? How much parameters can you make it learn? Okay. So all this kind of research is fantastic. It's very interesting. It's extremely technical. I cannot say to you that not. Okay. Sorry, let me skip this for the benefit of time. But the main problems are practical. Okay. Apart from the implementation, often the implementation is available open source, but it's not in Unity or Unreal or something that you can easily adapt for virtual reality or video games. It's in obscure research-oriented physics engines like Bullet or Mujoko or Dart, okay? And the characters are not ragdoll, they're not real characters, they're ragdolls, which is not very practical if you want to add blend shapes, like I think Maru will explain later, to also have facial expressions added to them, okay? So this makes it very difficult to integrate in a video game or in a virtual reality experience. So the Marathon project basically tries to solve this gap. It's something that is completely open source. You can download it. It compiles for Windows, Linux, and even Mac. I've tried it. So this is not something that I started. It already existed and I kind of picked it up. I tried it to make modular. So and put kind of clarify and simplify how it was used and progressively adding more benchmarks. There is if you are interested in going into physics-based animation, last year we did a full 1 year video recorded tutorial where it explains how to design a physics-based character, what you need to take into account, etc. And it's done inside the Marathon environment, so it's a very good way to start. Then there's also a bunch of basic benchmarks where it learns to do basic tasks. This maybe it's not so interesting for VR, but it's a good way to get started. Then there's also a way to basically create your own physics-based animation controllers. To do this, you import the real character with the animations as you do usually. And then you basically add some references like this is the head, this is the feet, this is the, etc. And you can make it basically learn very easily. to imitate the reference animation and move around in imitating the animations that you did, but in a physical way, which means that it will collide or it will have a bit more variability, which is something that feels nicer. So here, the kind of result that you will get is that you will have a reference animation, which here is in violet, and then you will have a ragdoll, which are these balls that have colliders that will imitate that, but will have more kind of will make more physical sense. And then we map it back to a rig character. So you can add, I mean, it looks nice, and you can add the facial expressions or all the other non-bodily centered things, okay? The ongoing work that we're doing now is that I'm trying to implement a richer control, interactive control. So the paper I showed you where they managed to parameterize like this, the rotation and the heat, so that these characters, I can ask them to control several things. For VR, for example, something relevant would be social distance or imitate yourself or some things like this. And also I'm trying to compare it with the benchmarks in the physics engines that are more generally used, to be able to say, oh, this works kind of in this as well or not as well as the reference animations that exist. Thank you. If you have questions.
I think this is super cool. How much does it depend on the mapping of the avatar and how much you can transfer to other bone systems? Or you need to retrain?
Actually, it doesn't depend. So this one here, so normally you need to retrain, okay? There's two ways to do this. First is I create the kinematic controller, or I put a big database of animations, and then I train for one character, okay? If I change the bone topology, so my body becomes yours, for example, which we don't have exactly the same size, then you need to retrain. This is a pain in the ass, okay? But this paper, okay, which kind of explores all kinds of possible parameterizations, one thing that you can do is, instead of changing the target position where you want the kick, is change parametrically, for example, the bone length, okay? Mm-hmm. And in this way, if it learns in this way, then on runtime, you could stretch it around, and then you don't need to retrain, okay? But it's, I mean, right now, there's 3 or 4 labs that are dead on this, but it's super technical, and it's in obscure engines like things that are not usable for VR. So there's a significant, let's say, translation effort that is going on.
Yeah, I will reach out to you because I think I have a lot of motions that work with the Rocketbox avatars, and I think we could train some physics-based for them. Okay.
To set up a training is 10 minutes, but then you need to maybe wait for 1 day to see what are the results.
Okay.
Or
yeah, interesting. Okay, sounds cool. Someone has more questions for John? Okay, we'll move to the next one. I think Matias.
How do I stop sharing? Have I stopped? No, I'm still sharing. Huh?
Yeah, so.
How do I stop this thing? Oops.
Okay, I did it for you.
Thanks.
Okay, let me share. I need to share sound, or it's automatically?
Usually you have to do it separately.
I got it, thanks. Okay. Almost there. Screen. All right, you should be seeing my screen right now.
Yes.
Yes. Okay, thank you. Sorry for that. Okay, my name is Matias. I'm going to be presenting the work that Mar, Eyolofek, Ken Jackback and Sean Brunner worked on. The title of this presentation is Headbox, a facial blend shape animation toolkit for the Microsoft Rocketbox library. I'm currently doing a postdoc at Northeastern University in Boston. So basically, what we've done in this work is we develop a system and a pipeline for adding and basically transferring facial expressions to the Rocketbox agents, right? For those that have no idea what it is, I think you do, but still I'm gonna basically detail what it is. The Rocketbox library is a free library of agents or 3D virtual humans. Currently, there are 115 agents that are fully rigged, facial embody, and this is a great tool because they have a medium to high fidelity, and they represent different occupations. We have males, we have females, we have different races, and it's open access, basically it's free. Everybody can access to this tool. So currently, the Rocketbox agents, they support and they can, basically you can plug motion capture animation. It's really straightforward. This has been done in Unity, and that's some example animation of a waving. So this is a really valuable library and it's free, right? As researchers, we are, at least me, I'm all the time looking for free, open, available tools to conduct my studies. My specialty is virtual humans, so this is a great tool. However, it had a limitation. It didn't have all these 115 agents, they didn't have facial expressions, right? And this is important for social interactions when you are in virtual reality or non-immersive virtual reality systems, and you want to have a conversation with these agents. You need lip sync, you need them to express emotions. So this was a limitation, right? So what we did, we created facial expressions to the Rocketbox agents, right? So we went to the literature and we created different bisems, facial action units, facial expressions that are compatible with the Vive facial tracker, and some custom facial expressions. And this was great, but remember, we had 115 agents, right? You can create 1 to 1 character, that is fine. But when you have to basically transfer to all of the characters consistently, this was a problem. This was a challenge, right? So let me show you a final demo of the facial expressions, and then I'll go back a little bit.
Welcome to the Headbox. This is a toolkit to enable facial animations on the Rocketbox avatars. The demo that you're seeing now includes lip sync from the Oculus lip sync, enabled by blend shape bisems, and the open face for the rest of the facial tracking, including a bit the head movements, right? So I hope you enjoy it. There are many avatars you can use, and you can combine it also with the Movebox for recording of animations and replaying of animations.
So also we have different tools. That was basically MAR, that was open face, but this is Unity Mixamo and Oculus Lip Sync. The tools, basically these virtual agents, they support pretty much, it depends on the facial expressions you have and you want to create. Any lip sync tool that was open face. This is in Unity with the Oculus lip sync demo.
Hello everyone. I just wanted to say how happy I am that we are in this workshop promoting the use of open access tools and libraries for virtual reality. Have a great day.
So pretty much we have the lip sync capabilities for many plugins and assets in Unity.
Hello everyone.
So as I mentioned before, one thing is when you create these facial expressions to one character, but we have different characters, different topologies, right? Different bodies, we have different races. Different races, they have different shapes of the face, right? We have male, females, we have child. So it was a really interesting challenge to create facial expressions to one character and transfer them to all of them. And this is what we've done, right? So we created this tool. We use Maya and Python 2.7 and Python 3. We heavily use Maya 2020. I tested the tool in Maya 2022, so it works. The functions and all the content we use is really standard. And this was something we planned. It wasn't just random, right? We wanted to be really simple and we wanted to use the standard tools so everybody can use it. So they don't have to install any third-party applications. Basically, the workflow was in Maya, in a brand new scene, you manually create these facial expressions by manipulating the joints, in this case, the facial expressions, right? You save this data, and then basically you can keep a library of your facial expressions. Once you're done, you just press the button and you transfer to all of the characters, 115. The procedure, simplicity. You just run the script, manually model the facial expression, you save them, and you transfer them. At the end, just collect the characters with the facial expression. So here's a clip where I use this tool. By the way, I'm using JSON, so that is basically a standard also, JSON, Python. All of the facial expressions that we are saving, are stored as a JSON dictionaries. Basically, we can load them and we can basically get the translation, rotation, and the transform data from each of the joints and basically have a library of facial expression, right? By the way, this can be applied to any type of position of the joints. So we can have also body postures. This is only for facial expressions. Then I just press transfer and I transfer to all of them, right? Simplicity was what we were looking for. It's a little bit, the process can be optimized. Remember, we have a lot of characters, but works great. So then you just load the character and you have them as blend shapes. Okay, and in this case, we have only 4 or 5 facial. This is just for the demo, but for the actual Rocketbox agents, we have 110 facial expressions. This is the graphical user interface. Again, really simple. You select the root directory, an input box for saving the name of the facial expressions, the list, transfer. Only 3 buttons. In all, this is our contribution in this with this workshop, this tool. We developed the system for creating facial expressions through the Rocketbox agents. This is freely available, both the agents and also the tools. Okay? So if you have any question, I'll be happy to answer. And if you want the tool, please contact me. I have the script for everyone.
Yeah, in principle, we will have it on GitHub. We're also planning to have the documentation of each of the blend shapes, so you don't need to open it and start going like it's very visual. Oh, this blend shape is this one. And we really wanted to follow the action units standard, so you can transfer to other avatars if you don't want to use these ones, or so it'd be very easy.
I have a question. Can you generalize it, like in terms of arbitrary avatars, maybe through training or physical-based modeling?
So the functionality is really simple, right? If you have these avatars, they have the same joint structure. With some tweaking, you could, right? And now I'm using Maya API when it comes to Python, but basically I'm just selecting joints. storing data in JSONs and loading and then transferring, right? If you take the same concept in Blender, it should work in theory, right? The only thing that you will have to adapt is the Blender, they have another API, another commands for selecting joints, but in theory, everything should work. Yes.
Okay, sounds good. We're gonna move to the last presentation. Lisa.
Yeah, hi. Let me just share my screen. Can I share my screen? Yeah. Can everyone see my screen? Okay, perfect. Thanks for having me. I'm gonna finish with the integration of Rocketbox Avatar in Ubiq. So my name is Lisa and I'm a PhD student in University College London. So here I'm also presenting for the rest of my group, the VCG group and Anthony's team. So first of all, something we haven't talked today is social virtual reality and their challenges. So social VR, they are virtual worlds where people can meet, interact, collaborate, and share experience and activities. So far, it has been used a lot in the past few years and growing popularity, especially since the beginning of COVID-19. The problem is that we have seen a wide variety of social VR applications being developed over the few years. And one of the problems we talked about and why we're talking today about open access tool is the lack of standards. In social VR, we have like a standard regarding the user representation, so avatars, but also navigation techniques, interaction with other users, with the world, with objects. And just to conclude, social VR needs to be more inclusive, trusted, and safe for the users. Basically, there's a lot of things happening and users are kind of lost in the middle of that. That's one of the reasons why the virtual environment and computer graphics laboratory at UCL developed Ubiq. Our primary goal is to have some platform for researchers and for teachers to be able to create their own social virtual experiments. One, to be able to run experiments, but also to be able to teach their own students and have them build their own project. That's what we've been doing on school. What's nice with Ubiq is that it's supported by multiple platforms, such as VR, but also desktop, and recently on WebXR. So how is Ubiq working? You can basically, like you can send the picture, connect to rooms where you just like select the avatar you want, put your name, and then with some code for the room, join your friend. Regarding avatars in Ubiq, so far we've been using mostly and show to the public this type of avatar. So they are floating avatars with basic heads and floating body and hands. When users are talking to each other, you can see some kind of icon, but we don't have yet any animation of the face. And that's why we want to integrate some other avatars. So we've been looking at the Microsoft solution with the Rocketbox avatar. First of all, because they're open source and they've been developed for many years now, and because they offer a wide variety of different avatars with different gender, race, and jobs. Also, you can have like fully rigged characters, both for the body and for facial animation, which are something we are interested in Ubiq. That's one of the reasons why we use the Rocketbox avatar. As you can see on the picture on the left, the avatar we are currently using are really simple and kind of like non-verbal cues, and it's really hard for users to be able to understand how they can understand each other. So having different type of avatar will help us having different type of social cues, which is something we are interested in social evaluation of interaction between people in social VR. To be able to implement the Rocketbox avatar, it's not really that complicated on Ubiq. You just need to put one of the Rocketbox avatars, a game object, on Unity to have an animator component. And then we have different scripts in C# on Unity to be able to set our avatar as a networked object, which will have a unique peer ID, and to be able also to send hands, position and rotation over the network. Like this, user will be able to see each other and also be able to communicate, because information will be sent over the network. Finally, we mentioned a bit earlier, mostly during my presentation, the Movebox toolkit, also developed by Microsoft. That's something we started to implement it at the beginning in Ubiq, but so far the VR solution is not the most proficient for social interaction, because they mostly cover head movement and hands movement, but not so far for the feet position. So right now we're using Final IK solution, which is not open access, but we are looking at some solution to be able to have also feet animation. So the virtual reality inverse kinematic solution is basically working on the dragging system where yeah, the feet just gonna drag and gonna follow the position of the belly of the avatar. So that's an example of what you can see from Unity with the Rocketbox avatar. Basically, right now we've been using the Rocketbox avatar to be able to work on replication of past studies. So we've been looking at past studies for social interaction in virtual reality and try to use the Rocketbox avatar. So it has been working just well, and we want to pursue our studies to be able to invest on the impacts of avatar customization and mixed group. Indeed, for social evaluation of interaction in VR, it's not only the representation of oneself that is important, but also the presentation of others that is important. That's why having an interest in avatar in social virtual reality is really important, because not just about one user, but about the group's dynamic. Also using avatars in Ubiq, it's really interesting for the group to be able to have some simple tools for experimenter to be able to control their experiments. For example, we implemented some simple tools to be able to mute and unmute users, but also to control the visibility like this using a software like Ubiq instead of using something commercial like Rec Room or AdSpace VR, is enabling the experimenter to control their users, to control privacy systems, and also to be able to collect data in Ubiq. Right now, what we were interested in and why we're using the Rocketbox avatar is to be able to work on the role of avatar realism, the customization, and also to see how dynamic of different social groups and mixed groups of avatar are working in VR. And we would like also to work on longitudinal study to be able to know how the customization of avatar and personalization of oneself can influence the interaction of people in VR. Where we would like to see in the future, and we would like to see also in commercialized social VR platform, is for experimenter to be able to moderate controls, but also for user to be able to control their own privacy. We would like to implement in Rocketbox avatars some bubble mechanism, but also set distances and invisibility control, those for users to feel safe and trustworthy within Ubiq. Also, emotion expression is something really important in social VR. So I think with the last presentation of Matias, we're looking forward to be able to use some control of emotion and facial expression. And finally, as I mentioned before, using like a solution, and we'd like to work our own solution for fit animation that hopefully would be also open source. You can find us on with our website, but also tomorrow we have some tutorial to present the whole Ubiq system. So if you have some free time to your Saturday, please just drop by and come ask some questions. Thank you.
Okay, awesome. Anybody has questions? I have a question. Have you tried this already with more people? And I wonder how many people want to use the different types of avatars, if you can give us a bit of insight on this.
So basically, when I've been using the Rocketbox avatar, it was either for 2 people or 3 people to interact with. So with 2 people, it's been interesting because it was either they had the same type of avatar and then they wouldn't even mind having either realistic avatar or something really cartoony without fits. But whenever you augment the number of people interacting together, they're going to look at differences. Like I have a Rocketbox avatar, but the 2 other people have something really cartoony. They'll be wondering, why is there a difference? And lastly, to answer also your question, with something really realistic, people would kind of expect an avatar that look like them, when realistic avatar and realistic one don't look like us, so it's not really a problem. But as it gets closer to the reality, we want it to be closer to the way we look like, so it's kind of a problem.
Yeah, sounds reasonable. Okay, I think we can move on to the gather.tom. There is a link on the Discord. There is a link also in the chat here. In principle, everybody should be able to join, and we will have a bit of a closing ceremony there. So see you there in a second. I'm already in. If somebody has problems, just let me know.
Bye-bye.
Bye, thank you.